Hi everyone, and welcome back to another CS202 online video. Today we're going to keep talking about recursion. If you just came back from the last video, we're just going to pick up right from there. So we ended the video talking about our first proper recursive function, which was this one. It doesn't do much, but it is recursive, and it's not infinite. It ends, right? So to refresh your mind, we got our function called foo, and we want it to print the number 1 10 times. And so what I'm going to go ahead and do here is I am just going to have it print out 1 at a time, and then it's going to call itself. And when it reaches 10 times, by using I to remember how many times it has run, then it will go ahead and terminate. And so, yeah, it works pretty well. However, as we have it set up right now, it's going to always be sort of hard-coded to 10. So I think as a good way to kind of give you an additional example of recursion is, let's go ahead and tweak this example and make the parameter that we pass in be actually the number of times that we want it to basically repeat. Because that's something you would want to do with a loop, right? You want to control how many times something repeats. Because, I mean, if it's always going to be 10, why do this at all? Why not just hard code it, or literally hard code, just literally print out 10 ones and call it a day, right? So let's go ahead and do that. And then from there, we can kind of expand our knowledge of recursion and do more examples and talk about a couple of other important things that I want to make sure I cover with recursion before we move on. So the goal is going to be, again, to take this function or to make a function that is going to be able, you're going to be able to pass in as a parameter. In fact, let's make 2 parameters. Let's make the first parameter be how many times you want it to repeat, and make the second parameter be what you want printed out, just because you can. Okay? So we are going to keep the name of foo for our function. So I'll just, I'm going to rewrite the word void because it's not as clean. There we go. And so I'm going to have the first parameter be the amount of times that I want it to print out. So it's going to be an integer. And I'm going to call that amount, just because amount of times or something. Okay? Or maybe R for repeats, just so I don't have to write amount every single time I refer to the variable. Yeah. Okay. Now, before you saw this equals 0, that's because I was using a default parameter. I guess it's always a good idea to protect yourself to have a default. But in this case, if I just don't put anything, then I'm going to force the user to pass in something. So yeah, I'll just leave it like that. And then my second parameter is going to be a specific character that I want the user to print out. Or I'm sorry, that I want the user to pass me in, which is what I'm going to repeat. So it might be a 1, but it might also be a letter, or whatever you want it to be. It could be even a string, but I'm going to keep it with a car because we don't use those a lot. And I'll just, very original to just use C for that. Okay, so what I'm going to do now to modify for my code is I'm still going to have a cout statement. So I will bring this up. But of course, instead of couting the 1, I'm going to cout my C. And remember that a recursive function has 3 main components: the recursive call, the base case, and then doing something to get you to your goal, which in this case is printing one of the repetitions of what you're trying to print X amount of times. So, or in this case, not X, but R amount of times. So the order matters of those things, though, and it's not going to be in the order that I stated it. The order is typically going to be, you have your base case before your recursive call. You have to have that. And then your do something can really be anywhere. It could be at the top, so before the base case, I suppose, yeah. It could be after the base case. It could even be after the recursive call. So the do something can be anywhere in the function. But typically, yeah, not typically, yeah, because I mean, really, it really depends on what you're doing. And I'm going to show you examples of that and how it affects it. In this case, it actually doesn't matter much, with one slight exception to that. So we got to do something, and now we still want to have the same recursive call, but it has two parameters this time. So for the recursive call, in this case, actually here, no, let's not, before I talk about the recursive call, let's talk about the base case. So our base case is not going to work anymore because our base case was counting up. So I'm going to propose a different way of looking at this so that we can still get this working and still use that R parameter as the number of times that we want it to repeat. And that is, instead of counting up, why don't we count, surprise, surprise, down? Okay? So instead of building up from like a 0 to a 10, in this case, we pass in the 10 as a parameter, and then we count down to 0, and 0 is our sign to stop. So yeah, let's just go ahead and do that. And say if R is less than or equal to 0, then we stop. Could I make it 0? Could I make it less than 0? Or less than equal or less than? Well, the difference is going to be whether you want that extra printout or not. If you want it to print 10 times, I suppose the ideal thing would be to have it print out at the t is going to go at 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Yeah, so I guess equal to 0. That way it doesn't print out 11 times, I think. We can test it later. But yeah, so as long as we do that, then it's going to stop when it reaches 0, and then it's going to immediately call the return, which is going to start that unwinding process of the call stack, right? And then a recursive case, like I said, because we are counting down, then instead of doing the plus plus I, we are going to do a subtraction, right? So we have two parameters. The first parameter is going to be consistent, so you just pass the same thing again, just a C, unless you want to actually print out a different character each time based on the count. You could do that by doing some ASCII math, I suppose, and adding the value of R to C, and then you would see like a alphabet. You know, if you pass in like the letter G, then it's going to print it out in reverse of the alphabet, right? It's going to be like, oh god, now I have to give you guys the alphabet backwards, right? So it's going to be like F, E, D, C, B, A or something. And then after that, it's going to go to whatever is less than an A, probably the numbers in the ASCII table. So like 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, and so on. So yeah. But right now we're just going to print out the same character. So we'll leave that the same. But we could do that. We could modify it here. And like I said, in this case, we're subtracting from 1. So there's a lot of ways you can do that. You could do R minus 1. You could do minus R. The one you do not want to do is this one, right? Because that would not give you the value less than R. So like if R was equal to 5, then this function would get called with 5 again, and then you would have this infinite repetition happening, because that's how post decrement works. So I'm going to go with R minus 1 this time, just because the last time I used the increment operator. So yeah, that's my recursive call. And then we have your closing curly braces, and here you go. Whenever we call this function, so if in main, if I say something like foo 5, then what's going to happen is, well, I suppose pass in a character as well. So let's just say I'll pass out the character A. So what's going to get printed out of the terminal is going to essentially be a bunch of A's. Now, how many A's we're going to get printed out? Well, let's actually work it out by hand. So in this case, it's going to go in here and it's going to print it out once. So let's just write out once here. And then let's just kind of keep track of the value of R, which has R equal to 5. And then we know A is always, C is going to always be A, so no need to keep track of that. We're doing this check. We can see that R is greater than or equal to 0. Ooh, snap. I think we put that backwards here. If R is greater than or 0, return. So it's actually going to return right now. So this is not going to work. So this is where you check your code. I suppose that this should be less than or equal to 0. Because now, you know, when it gets to 0, it stops, but before it doesn't, right? So see, it's always good to review your code. So in this case now, 5 is not less than or equal to 0, so it'll keep going. And then we're going to call it with 4 instead of our having 5. So now we'll switch that to a 4. Okay, so from there it's going to print it out again. This is going to check if 4 is 4 less than or equal to 0. No, it's not, so it's going to skip that. And it's going to call it with a 3 now. And so it's going to print out again. It's going to do the check, and then it's going to call it with a 2. It's going to print out again. It's going to do the check, and then it's going to call it with a 1. It's going to print it out again. It's going to do the check now, and it's still going to be 1. So it's going to keep going, right? Because at first it was a 5 for this one, and the 4, and the 3, and then the 2, and then the 1. So now it's going to do it again and call it with a 0. However, because the Z out or the do something is before the base case, we're actually going to get it a 6th time printed out, which perhaps is not what we wanted, because maybe we, when we said 5, we meant 5, not 6. Okay, so in this case, it's going to print out the 6th time. Then it's going to read the if statement. It's going to say, okay, well, 0 is definitely equal to 0, so then return. And then it will not call the function call again. So at that point, it's going to return to the previous call when f was a 1, or when r was a 1. It's going to finish that code, which does nothing else, and then go back again to the other one, finish, go back, basically that upwards unwinding until it gets back to whoever was this function call from, which could have been main or another function. So we have 6, right? So how do we fix that if we wanted to have 5? There's a couple of ways. One of them is we could just switch this to a 1 and then call it a day on that. We could also switch it to a 2 and I suppose make it less than instead of less than or equal to. Or I think this is personally the way that I might like this better, is we could flip the position of the do something and the base case. So just copy it again. What I could do is I could go ahead and, hold on, let me get out of the arrows. I could take this, move it up here. Okay, so what I can do is I can just move this beneath the base case. Check. So now it's going to run the same until it gets to the 0. But when it gets to the 0, it's going to do this check first, which means then it'll return at that point instead of printing this out. And that'll get rid of that extra A being printed out, or whatever the character may be. So is this an inherently different concept or something? No, it's still recursion, but you start to kind of see that the way you order these things matters. So I know for sure, I think you kind of believe me in the fact that the base case should always be before the recursive case, otherwise the base case will never be checked and this thing will run forever. But what you might have been wondering is well, what about the do something? If the base case has to go before the recursive case, then I can't really flip the order of this and this. But this, on the other hand, could go anywhere. It could go here, it could go here, or it could even go here. So you've already seen the difference of what happens if I put it here and here, right? Now, what if I go ahead and were to put this at the bottom? So let's see what would happen then. So instead of doing it like this, let us move this to the complete bottom of the code after the recursive call. So in this case, this is going to basically not print anything until it actually hits the base case, right? So let's say we call this foo with a 3. Okay? So when we call it with a 3, and I guess give it a character as well. So let's do a B this time. So in this case, R contains a 3 at the beginning, and when it runs, it starts, it checks the base case. 3 is definitely not less than or equal to 0, so it skips that. And then immediately it goes to the recursive call. So the execution stops right here, and it makes a brand new foo instance. So in the call stack, I'm going to abbreviate an F for foo, and an M for like main. We'll just imagine that's the function that called foo initially. So like this one is main. So I'm going to just assume, or imagine that's the case. So it's going to go to F. And so now that we're in F, we see the initial recursive call, which makes a second instance of F. But in that second instance of F, in this case here, initially there was a 3 passed in. And this one, there's going to be a 2 passed in because it's r minus 1, right? And now it's going to do the check. And it's going to see if 2 is less than or equal to 0, which is not. So in that case, it's going to go on, it's going to see another recursive call and make yet another F, in which case this one's going to have an F1. Same scenario, is still not less than or equal to 0, and it's going to go to the recursive call and make another F. See, there's no printing going on right now. We go to 0. Now, when r is equal to 0, then we hit the base case, and we see that r is less than or equal to 0. So in this case, return. So now, even though we were here, we're going to do it with a different color. We go back to here now. And in that case, we were just here. So now we can run at the next line, which is the actual print. So now, as we're unwinding the recursion is when we're actually going to do our something, in this case, printing. So now we're going to see the first letter get printed out. What does that say? C? Oh, because it's the name of the character, yeah. So in this case, it's going to be our first B printed. And then that function is going to end, and so this is going to unwind further to here. And now again, it's going to basically start from here and then follow to the next line, which is that one. And so we're going to get another B. And in a few minutes, I'm going to run the debugger, and you'll get to see this actually happen live. So, okay, we got that done, and then it unwinds again to this one. And again, it prints out a B, and then comes back. And now we're back in main, and we can see that we had only 3 printed out, which is nice. That's kind of what we expected, or what we hoped for. Not expected, but what we hoped for, because we have a 3 there. However, even though there's only 3 Bs printed out, I want to emphasize that there were 4 instances of F created at one point. It's just that the bottom one, so this F0, that never reached the part of the printing because it reached the return first because the base case was first. And so this is something to keep in mind so that your things line up as you expect. You have to make sure you understand what the differences are between putting your do something after the base case or before the base case, or before the recursive case or after the recursive case, because it's going to affect how the code runs. There is a name for having your do something before or after the recursive call, which is something that I very, very briefly mentioned in the last video, and I said I would explain later, and that later is now. And it's going to be the tail and head recursion. So go ahead and define those. Oh, come on, I'm trying to change the color back to black here, so just because other colors might be harder to read or something. So there we go. Tail recursion and head recursion, and these concepts are actually like, they even go beyond programming, by the way. So when you get to like 326 or even compilers or like, you know, semantics and regular expressions and all these fancy cool things, like these will come into play in those too. So recursion goes beyond just programming. It's a very, and you'll see that in an example here pretty soon as well. So it's in your benefit to actually like to kind of understand these things. So at least if what you want to do is computer science. But yeah, so in this case, if I go up here to my recursive function definition, I'm going to copy this and I'm going to paste it down here. Okay, so maybe I'll put them side by side. Head recursion and tail recursion. So when it comes to head and tail recursion, you're still always going to have, so I have them right now the same, but I'll edit it in a minute. So you're always still going to have the base case always be before the recursive case. Like that is a must. Like this is definitely a must. Okay, regardless. Because otherwise you're going to go infinite, which is not good. But where it matters is where your do something is placed, okay? In the case of head recursion, you are going to first go as deep as you can in the recursion, and then on the way out, that's when you're going to head ahead and do your progress. So that's like the example that we just did, where we have the see out after the recursive call. Whereas for tail recursion is what we did last class. And that is a scenario where your recursive case is actually the last thing in your function. Like this. And that's more, I guess, easier to kind of think on your head, because like normally when you're thinking like I'm gonna go do something, you're like I'm gonna go step 1, step 2, step 3, step 4 and do it that way. Whereas the other way around is like you're going to go as deep as you can, and on the way out you're going to do things. That's kind of like a backwards mentality to what we're used to. But it actually turns out that there's a lot of really good, like really cool algorithms that involve that mentality and make it a lot easier. When you, again, I mentioned this last time, but I'll mention it again, when you see how traversals work in binary trees and 302, and you see the different kinds of traversals and things like that, you kind of get a better sense of why head recursion is such a nice thing to have. It also helps you to remember. So remember that in your call stack, you save the parameters, so like the local variables and the arguments that are passed into a function. You save that as you're making a new instance of the function. So when you're unwinding it, you're able to remember this. And furthermore, you can actually pass things on the way out as well. So you've already seen how to use the function parameters here to pass things into your functions, like, you know, how we're keeping track of the R here. You can also use that parameter on the way out of the recursion. However, you can't really edit what has been already set. Right? So like if I have a function call where r is equal to 2, and then I have a function call here at the bottom where r is equal to 1, can't I modify this r up here from the 2 in the 1 call? So like I have like, so maybe to make this easier, so I have a foo here where my r is equal to 2, and it makes a call for a foo where the r is equal to 1. Can I modify this 2 from here? So can I do that cross connection? And the answer is yes, kinda. There's a way to do it, and that is if you're dealing with pointers and all you're passing in are addresses. So in this case, let's say R was a pointer and it's pointing to some dynamic memory location. Then in theory, yes, you can actually do that because they're both referencing the same thing. But in practice, it's going to be very problematic if they are, because you're going to be overwriting it when you pass it in with 1. So you would have lost it too. So there's a much better way of doing this, and that's using your return value. So you can use your return value to communicate information back up the chain. So a lot of the times when you see head recursion where it goes really deep and then it comes back out, it's combined with the return value to be able to feed information back as you go up. So let's kind of see how you could do that. So for my next trick, I'm going to come up with a function that is going to count the numbers in an array. Yeah, I think that one will be a decent example. We can do it both ways, but I'll do it at least with a return value. Okay, so I'm going to have a function that's just going to be called count. And this function's job is going to take an array. So I guess an integer array. One-dimensional array, so we're just using that. I could use the square brackets, but no fun there. And so what I want to do is I want to pass in some array, and I suppose, you know, to make my life easy, like you all got to probably play with some assignments where you get to count the arrays, but let's just make our life easy. Let's pass in the size of the array as well. Okay, that way I can count the array without like having a headache of figuring out where the array starts and ends instead of checking for null or something. So we have the size. Okay, so given the size of the array, I want to basically count the contents of the array. So if I have an array of size 4, and maybe this has a 1, a 3, a 4, and another 1, what I want to get back from this is basically a 9, right? Because 1 plus 3 is 4, plus 4 is 8, plus 1 is 9. And so I want to do it recursively. Could I do it iteratively? Yes, I could. I could just do a little while loop that counts, you know, that counts each spot and keeps a count of that. And when it's done, it just prints it out or returns it, right? And like I said, I mean, that's the whole point. It's really hard to teach you recursion and jump right into the examples that really benefit from it, because they're usually pretty abstract and harder. So again, don't feel like, oh, you know, why are we doing this with recursion when like I could have done this with a while loop in like 5 seconds. I know, but that's not the point. I'm teaching you with easy examples, because if I just popped up here and started showing you quicksort, you would all freak out and like be like, I'm so confused, which is fine, because I mean, you'd be trying to learn both quicksort and recursion at the same time, which would not end well for the most part. So yeah, but okay. So, you know, we still want to have our 3 things, our base case. So I'm going to take the concept that I took from before, which was to count down, just to avoid having an additional variable in here to be able to keep track of where I am in the array. So I'm going to count that. And I want to return the result and count. So my function call to this is going to be something like cnt array A, and the size is, well, 4, right? 4 for that array that we put. Okay, so the base case. My base case is going to be when s is basically equal to less than 0, I suppose, or well, equal to 0. So I like to play it safe and put less than or equal to 0, but equal to 0 would be fine. Just, I suppose, in case somebody tries to be tricky and pass in a negative number for some reason to avoid a sec fault, I suppose that would save you. So yeah, okay. So if that's the case, then I'm going to go ahead and return. In this case, I got to return the value that I want. So what is that value going to be actually? Like what am I going to return there if I'm done? Like I need to return a number, right? And that number should ideally be like what the final addition is, right? So we're going to revisit that in a second, but for now we'll let it be like that, okay? So yes, we still need to add some sort of return value there, and hopefully it's the addition, but we'll kind of come back to that. So again, this is my base case. Okay, moving on, the recursive case is going to be the function itself. I could use pointer arithmetics to also move around with the pointer there, but I'm not going to do that. I don't want to make this harder than it has to be. And I'm also going to go ahead and just pass in s minus 1. Okay, so that's my recursive case. And finally, you might do something, which is to add the current index that I'm looking at so that I can return that afterwards. Okay? So how do I do that? Well, I can simply do this. However, it's going to run into a problem. If I'm passing in the size, you know, if you look at the indices of these things, this is like index 0, 1, 2, and 3. So if I pass in 4, that's out of bounds, right? So I want to make sure that I'm actually accessing s-1 every single time. And that's also going to avoid issues here because, as you can see, I'm returning when it's 0, but 0 is a valid index. But because we're doing the -1 trig, we'll never see that happen. Okay? So now the first thing you got to figure out is, okay, I know that I can get, like, if I have some valid integer t for temp equal to that, I know that I can get that specific spot. But how do I add them all together and then return the result? Okay, well, what you can do is you can take the current value and then add that to the next value, right? So I know that when I'm done with this, I want to return this value, which is the current spot I'm looking at, plus all previous values as well, right? How do I get all previous values? Well, I can just do the function call that I have up here. So I could just go ahead and do this function call, right? So let me move this a little bit more so it fits. And as long as I guarantee that that function call is going to return the right value, then I'm okay. However, right now it's not returning anything. Well, that's because when you hit a negative value, you don't want to add anything to the array because you're out of bounds. So why don't we just return a 0 to avoid adding invalid information? Okay, I can do that. Cool. What else? Nothing else. I'm actually done. Yeah, this is it. So let's look at this carefully in case I lost you for a second here. So what we did is we kind of combined the do something case or the do something and the recursion, the recursive call within one line of code. In fact, I could even like combine this further and simply say like if s is greater than 0, do this and then else return 0. I could do that too, but that'd be just kind of weird and make it unnecessarily complex. So I think this is the cleanest way to do this. So let's understand what is happening here. Our base case says that yes, when we reach 0, we stop because we know that we're looking at 1 less than what the index is. We don't want to look at negative indices, so that's fine too. I think we understand that with the exception of why we're returning a 0 here. But the reason is because we always want to return what the value is of that index. And for a valid index, we just return that index itself, which you see here, -1 to avoid the issues with the offset. But when it's an invalid index, we don't want to add additional numbers or subtract additional numbers because there's nothing valid, right? So that's why we get a 0 here. What is weird too is you have a plus here. So what I'm saying is that this whole thing is an addition. We're going to take the current spot that we're looking at, which is this one here. This -1 is again because at the beginning when we start with 4, we subtract 1 to get 3 so we can look at this number. So we're going to look at that number 1. So this, when we do the first call here, so when we say CNT A4, so I'm just going to say when we do CMT4 here, it's going to look at this line and it's going to skip it because s is greater than 0 right now, so we're fine. And then it's going to see here, it's going to say return AS1 plus CNT AS -1. And so that is going to basically say return spot S -1, so 3, so index 3, so return the value of 1, so this index value here. So 1 plus whatever the CNT for 3 is, right? Because S -1 is 3. But we don't know what this is. It's going to do another function call for that. That function call is going to go through this. And again, it's going to be like, well, it's greater than 0, so we're going to keep going. And it's going to see the return statement, and that CNT, so this is going to basically return. So if this returns this, this one is going to return the current spot, so S is 3, so S -1 is 2, so it's going to spot A2, which happens to have a 4 in it. right? So this is spot A3, and this is spot A2, which has a 4 plus CNT at spot S minus 1, which is spot 3 minus 1, which is 2. Okay? So now we got to look at that one. So what is CNT2? Again, it's still greater than 0, so it doesn't go to the base case. So this one's going to return S minus 1, so 2 minus 1 is 1. So it's going to look at A1 now. And what's in A1? It's a 3. So we get a 3 plus CNT of S minus 1, which again, CNT right now is a 2. So it's just going to call CNT at 1. Okay? So that's going to come from that function call. And then this is going to have another function call. I'm running out of space there because it's kind of tilting this way. So let me just move it a little bit here. There we go. So now this one's going to have another call with 1, right? So now we're going to look at S. S is 1, so S is still not less than or equal to 0. So now we look at that. So 1 minus 1 is 0. So now we're looking at index 0, which is the first index, and that contains a 1 in it, plus CNT of 0. Now, CNT of 0 function call is going to go, so that S is equal to 0. So because S is less than or equal to 0, that is true. And it's just going to return a simple 8. Or sorry, 8. A simple 0. So this is just going to return a 0. Oh. Okay, so now that we know that CNT0 returns a 0, now we go back to here for this one, okay, for CNT1. Because remember, this here is CNT1 function, this is CNT2 function, this one is CNT3, and then this one's CNT4. Okay? I don't like that one's on the other side. Let's put it here. There, it looks more aesthetic that way. Okay? So now that we know that CNT0 evaluates as 0, then we can do the addition of 1 plus 0. 1 plus 0 is equal to 1. So this should return a 1. So we can return a 1 from this. Okay? So this 1 goes up and replaces this one here. Maybe use a different color for that. So this gets replaced with a 1. Just like this got replaced with a 0. So when we get that 1, now we can do 3 plus 1, which is 4. So this returns a 4. So then basically 3 plus 1. So it returns a 4, right? So this here returns a 4. And so now we do 4 plus 4. That returns an 8. So that goes up here, and this becomes an 8. Now we do 8 plus 1, which is, or 1 plus 8, which is 9. And that's what this gets back to main, is a 9, which is the correct value. So you see that? We're doing that on the way out of the function, or out of the function, the recursion. And so this is a really good example of head recursion, where you just go all the way to the end of the list, and then you count on the way out. This is also a great way to reverse a list too. You go all the way to the end, and then you print it backwards. Think about how you would do that with an array, or sorry, with a loop. You'd have to have a counter that counts backwards, right, from the end to the beginning. Here, you just go all the way to the end, and then as you own 1, you print it backwards. When we get to linked list in the next videos, eventually we're going to play with the linked lists, and you'll see that the only way to easily print out a linked list backwards is actually using recursion. So that'll be actually maybe the first real example where you'll see like, hey, recursion is the only way that I could have done this, unless I do something really nasty with like a stack. So yeah, I forgot about that one. Yeah, that'll be a good example. You get to become a believer of recursion, I suppose. Okay, so this sort of diagram that I did here is known as usually as a recursion tree, and they're very useful to try to visualize and keep track of how the recursion is happening so you don't get lost. Now obviously this is a very simple example, but like for more complicated stuff, this recursion tree it really helps you make sure you don't forget like which recursion level you're at and like what do you have to go back to and so on. So it's a nice little thing I recommend that you use when you're trying to decode what a function is doing without having to run it, or when you're trying to debug your code too. Okay, so all of this is just to show you the difference between head and tail recursion and what they do, and you know, when to use one or the other, really. Which is more of a question of like what you need for the given task at hand. So, yep, that's head and tail. One other thing I want to show you with recursion is kind of like indirect recursion. Yeah, let's do indirect recursion. This is kind of a really quickly like FYI kind of thing. So I think you understand the difference between recursive code and non-recursive code, right? Recursive code is the code that's going to call itself, just like non-stop until it hits that base case, right? So if I have a function like this, and I ask you, is this code recursive? Then your answer should be absolutely not. There's no function calls inside, right? In fact, the code's pretty random. Why'd have that random return there? I don't know. It felt right to do. I don't know. Okay, cool. What if you see the following code? Is this code recursive? I don't know. It might be actually. But the answer is definitely that you can't tell from the given information so far. Now, why is that the case? Because you have a function called to bar, and you don't know what bar is doing, or where he has been, or she has been. I don't know. So let's see what bar has been up to. I suppose for this code to compile, bar should be up here. Unless you do some sort of extern or prototype, but yeah, okay. So bar has some code in it. And yeah, that's it. That's all that bar does for now. In this case, I can resoundingly say that no, this code is not recursive at all. No worries. Not that recursive code is dangerous, but just, you know, just no worries that it might be recursive. Cool, but obviously if I switch to say something like this, you would say, oh yeah, definitely recursive, because like, well, maybe not foo itself, but technically in a way, indirectly I suppose, it's recursive because bar is recursive. So like once you hit bar, you're going in forever, right? That's going to recurse forever. And you're right, yeah, it's definitely recursive, at least bar is. But that's not really what I refer to when I'm talking about indirect recursion, actually. Indirect recursion is, imagine instead of bar being here, that you see a foo. Now things are kind of like, ooh, okay. So the code is recursive. Why is it recursive? Well, try to run the code, see what happens. It doesn't matter if you start in bar or in foo. If you start in foo, you're going to run some code, oops, and you're going to hit bar, so you're going to start running bar, and you hit foo, so you're going to run foo, and you're going to hit bar, it's going to run bar, it's going to run foo, and so you're going to basically back and forth, you're going to keep kind of like playing it like you're playing ping pong or tennis, just going back and forth, and they're going to basically recurse forever. Individually, each function might not look like they're recursive, but you know, they actually are. So why would you do this? Well, usually you wouldn't. It's more of like, why did you accidentally do this kind of thing? I'm not going to say like there are no algorithms that do this, because there probably are. probably make sense and they probably make your life easy. But for the most part, people do this kind of indirect recursion by accident. They don't realize that they're calling a function that is being called by the other function, and it might not be as obvious as this, obviously. But there might be a bunch of if statements, and like within one of those, or like imagine like a big switch statement, and in one of those switch statements, it actually like calls the function that called it. And there's that risk that given the special right circumstances, that you're just ping-ponging back and forth. That could happen. It's very bad, because now you're stuck forever. More than likely, you'll sec fault quickly. Something that we haven't seen because we haven't really like coded recursion on the computer is that recursion is pretty reliable to sec fault if you just let it run. Like you'll see it. Okay, so there's that. Indirect recursion. Be aware of it. It exists. Just keep your guard up about it. Okay. One more thing that I want to show you, and then you can jump in and code some stuff. Again, the coding part is just like you're just gonna code stuff and experiment, and like recursion is something you'll get and feel more familiar with only if you just start coding it. You just go for it, and just code as much as you want. I'm not saying that you should be coding stuff that you care about recursively unless you have to, but like for a while, just do a bunch of recursion so you can feel strong with it. And you'll see that the assignments are just going to be a lot of small recursion exercises just meant to get you going on the recursion hype train. Okay? So one more thing I want to show you. And this is again a case for why recursion is nice. So we're going to turn to our math colleagues for that. And that is because I want to show you Fibonacci. And Fibonacci is one of those things that like, whenever you see somebody give a recursion video online, they probably bring up Fibonacci because it's like the hello world of coding is like Fibonacci for recursion, right? So in case you don't know what Fibonacci series is, let me just very quickly go over it. So it can start with 2 1s, or it can start with a 0 or 1. I'm just going to go with 0 or 1. And basically, let me just write a couple of the numbers and then explain what they do. I'm actually computing this as I go. Uh, 34. Okay. Oops, let me make that nice. Okay. So what am I doing? Like, how do I come up with these numbers? They're not random. They might seem random, but they're not random. Actually, they probably don't seem random to you if you can, like, hopefully you don't see them. Like, you're all smart enough to kind of see the pattern, I hope. But let me tell you the pattern just in case. So the pattern here is that to calculate any number in the sequence, all you have to do is look at the previous 2 numbers and add them together. So for example, here 3 plus 5 is equal to 8. And if I want to compute, like, let's say this number, I take the previous 2 numbers and add them together. Now, there is one exception to this rule, and that is that you have to have a beginning to it. So you have to give it the first 2 numbers. So a lot of people will just give them 2 1s as the first numbers. In my little scenario, I'm giving it a 0 and a 1. So if I give it that, then it works. Why do you need to give it the first 2 numbers? Because the rule of Fibonacci is that the number is the result of the addition of the 2 previous numbers in the series. So numbers are infinite. So if you don't give it the 2 previous numbers, then it's never going to know what they are because there's infinite number behind. So like it will never be able to compute it. So that's why you just say that the first 2 numbers are these. 1 1 or 0 1. Okay? So it turns out that if you ask the mathematician to define this, they'll define it using a function. And they'll see something like this. So let's say that f of n, which represents the nth number of the Fibonacci sequence, is made up of the following rules. Come on. There we go. It's made up of the previous number plus the second previous number. So n minus 1 meaning the n minus 1th number. So like if this is the 5th number, you're looking at 5 minus 1, which is 4, so the previous one, the 4th number, plus n minus 2, which is 5 minus 2 is 3, so the 3rd number. So if you're computing the 5th number, you got to look at the 4th and 3rd number, add them together, and you're good to go. However, you're only going to do this as long as you're looking at the numbers bigger than 1. So like the second number, right? So if you want to compute the second number, you look at the first number and the 0th number. But if you're trying to compute the first number, then you do a special case, which is the 2 first numbers that you got to give it. So I'm going to say that my first 2 numbers are 0 and 1. So I'm going to say 1 for when n is equal to 1, and 0 for when n is equal to 0. So this is the mathematical representation of the Fibonacci sequence. Oh yeah, I should probably write Fibonacci since you're home. Well, that assumes that I can spell it, actually. Let's see if I can do that. So it's like Fibo. I think there's 2 C's. Maybe. Quick Google. Let's Google. Let's not offend Fibonacci. We hunted at night. Nope. We did not offend him. We spelled it correctly. He was Italian, by the way. Google just told me that when I searched. So thank you, Google. Very cool. I mean, well, no stereotypes, but the name felt Italian. So, yeah, okay. So, all right. Fibonacci sequence, mad representation of Fibonacci. Even if you didn't know what it was, I could give you this, and in theory, if you understand mathematics, you would understand that this is what Fibonacci does. If we're given f of n minus 1 plus f of n minus 2, add those 2 numbers together as long as n is greater than 1. That will give you the nth series of the number. For anything less than 1, you have the case of n equals to 1 and n equals to 0. In those cases, you get a 1 or a 0. Bam, done, moving on. Okay? Cool. All right, so the mathematician guy comes to you and says like, yo, I need a computer that can like, I need a piece of code that can compute the Fibonacci number for like whatever number I feed it, like 100. Can you do that? Well, to compute the 100 number, you got to compute all the ones before it, right? So you could probably write a iterative piece of code that could do this. In fact, I believe I have that somewhere in my notes from last semester, which I could just show you. Do I have it somewhere here? Yeah, here we go. I'm just gonna copy paste that because I don't want to use up all the time on this. And again, this is a recursive day, not an iterative day. Although last semester I did it on the fly, so you're more than welcome to see that. But yeah, this is kind of what it looks like, although this one's printing out the numbers. So I suppose you could remove the printing and then just print the last number that gets printed, or that gets computed before you finish. So maybe like after the for loop, you just see out next. Yeah. So probably just take this and put it outside the for loop. Also, I don't know why there's no curly braces for the for loop. But yeah, put some curly braces there. And I think that'll probably do it. You can play with this code and understand it later. But what I really want to emphasize for this class today is that you could do this Fibonacci recursively without really understanding how it works or why it works very easily. That's the power of recursion again, that you want it to help you, not to hinder you. Recursion is there to make your life easy as a programmer, not harder. And that's something that a lot of people kind of forget. Obviously, when you're learning things, they're usually hard because you're learning them. If it was easy, then you wouldn't have to really learn them. You could just do them or deduct them yourself, deduce them yourself. So with this, if you want to create your recursive function, you already have everything you need. The mathematician just kind of gave it to you. You have your base cases, which are the 2 bottom lines, so these 2. And then you have your recursive case, which is also your do something case because you have the addition. So turning this into an actual function is like super easy, like piece of cake easy. Like not even like, okay, easy but not really easy, just to motivate you to do things. But no, like this actually is really easy. So let's go ahead and do that really fast. So int fib for Fibonacci, and there's no real any parameters that you need for it, I suppose. Although no, maybe you want to pass in, yeah, you want to pass in the nth number that you're working with. So n, because remember there's a number here, so that's your parameter. Okay, and then the one thing I'm going to do different than the math person is I'm going to flip the order of these. So instead of putting this first and then these two, I'm going to flip. Actually, well, here, I'm not going to flip them at first, but then I'll simplify it and flip them. Okay, just to not confuse you. So we'll stick to the math way. So I know that I have to run that if n is greater than 1. So I'm going to say if n is greater than 1, run this code, which is fib n minus 1 plus fib n minus 2. I should have made this function be just f, so it matches completely. Let's just do that. So it matches really close. So it's called f. F in the chat. Okay? And then after that, I am going to, I suppose, since I'm really trying to match this like word for word, I'm going to put on 2 more if statements that says if n is equal to 1, return 0, or sorry, return 1. I also forgot to write the return here. And then I suppose if n is equal to 0, return 0. Okay, I'm done. GG, easy peasy, lemon squeezy kind of thing. Look at that. It literally looks just like the math representation. Like, it's so close. It's ridiculously close. So therein lies a bit of a power of recursion that you don't have to do a lot of thinking. You just code it how they give it to you and you're good. So when you're dealing with math people and they throw in these weird functions at you, just make them into functions and call it a day. Let them debug your code if a function is wrong, because that means their function is wrong. So yeah. However, I could make this a little cleaner. I mean, a lot cleaner actually. But I wanted to show you kind of like step 1 of the process is just to make it the same. And if you're in a hurry, yeah, it's good enough. You know, it compiles, it runs, it works. Yeah, whatever. But yeah, you can see that we have the function calls here. So instead of having 1 recursive call, we have 2 of them. So that's a step up in the difficulty level. So far you would have been doing just 1 recursive call, right, per like instance. But here you have 2 of them. You have the f-1 and f-2. And this is very inefficient, by the way, but you have it here. Let's simplify this. So one way that I could simplify this is, well, I could simply say that, you know, if n is less than 1, just return n. So here, let's just let's combine this. Whoa, I copied the big curly brace there. So I can say if n is greater than 1, then sure, go ahead and by the way, notice that the base case is kind of hidden in here, and the base case is the if statement here. That's your like hidden base case, the fact that that's there. It's not obvious anymore, and that's one thing that you'll see in recursion. The base case is always before the recursive case, but it might not be as obvious as seeing like an if statement with a return value. It's kind of hidden in there, but it's still there. You have some sort of conditional check before you see the recursion. It could even be hidden further if I had this at the bottom. So like if this was down here, it would be like even a little bit trickier to kind of see what was happening. But yeah, I could literally just say else and then just say return n at this point, right? Because we know that if it's n is equal to 1, it returns 1, n is equal to 0, it returns 0. So it always returns whatever n is equal to. The caveat with this is that if you pass it in like a negative number, this thing will break. But then again, that's not meant to be part of the sequence. And that would also break here because you would just return like, well, in fact, you get an error saying like, not an error, but probably a warning at the very least. Client might give you an error, but like saying like, yo, there's like potential that you have an uninitialized like values or no, that wouldn't be there. It would be like it would basically tell you like there's a chance that like you could have a return statement where it doesn't go into any of the if statements, and like it would freak out. So yeah, so that's still there, and that's more of a question of like cleaning your input and whatnot. But yeah, if you do that, this looks cleaner. Could it go cleaner than this? Not that I can see, but yeah, this is good enough as it is. I'm happy with it. Now, there is more to this Fibonacci example than I'm going to show you. In the second recursion video that I did in the, what is it? Fall 2021, I do what's known as a recursive tree, which I'm not going to do this semester, but I'm going to show you a picture of that. So I already showed you how to do the recursive tree for a single function, a single recursive call. But when it comes to two, you have like a left and a right. So if I'm trying to compute for fib4, this is actually what the recursive tree looks like. And it gets a little complicated. It takes quite a while to do, actually. One semester I did this in person on the board, and it took us like half the class to do it, just for a single example. So if you're interested in seeing how these work and how to use them, you're more than welcome to check that video out. I will leave a link in the description below of the YouTube video, so you can check it out. But for me, for this semester, I'm going to just end it on that for the Fibonacci example, and I want to use the last 15 minutes to code in the computer and show you recursion live. Okay, so let's go ahead and switch over to the computer. Okay, so let's go ahead and code let's code one of the examples that we did, just so you can see that first. So maybe let's do the printing out of the list. That one was nice. I like the list one. Okay, so I'm gonna just count and the A into S, and then I said if S is less than or equal to 0, return 0, which is my base case. Otherwise, return A S minus 1 plus CNT A S minus 1. Okay. So all that remains is the initial call, which is going to be A4, which is my size. And I guess I gotta make the array A. So let's just put in it's an integer array. Let's make it dynamic. So otherwise this might complain. I was going to make it a static array, but then it's going to say it's a const array, and it's going to make me, yeah, let's do that, because then I can show you that. If it does complain about that, I'll show you how to work around that if it yells at me. So 1, 3, 4, 1. So I think it's going to yell at me that I have to do a const. But maybe it might not. Let's just see. Oh no, it didn't yell at me. That's cool. I thought it might. Because this is like the way I set this up, it makes it a const. It's like literal. So it yells at me. But it didn't yell at me, so I'll take it. Okay, let's see out the result so we can see it. So you can see the 9. Perfect. Now let's go ahead and put a breakpoint so we can actually see the code run. And by the way, all this semester, the word call stack, look at that, has been there all along. Now you know what it is for if you didn't. But I think I might have mentioned it before, the recursion stuff too. Okay, so trusty debugger, please lead the way. So we make our array, so we can see that we have our array here. It has the 1, 3, the 4, and the 1. And then we are going to enter the recursion. So you can see the call stack from main line 11, it went into the count function, okay? From there, it's going to take the check of s being what the value of s is compared to 0. So if s is less than equal to 0, it's going to return, but it has a 4, so it's going to keep going. And now it's going to return the summation of the current value of this plus this function call. This s has a 4, so that means it's going to look at A3, which you know, kind of lost the pointer there to see it, but you saw that it contained the values. If we run this, that's freaking out. It's fine. You can see that that made another function call. So you see the call stack now, it's growing. I know I kind of do it the other way in my example. Here it's going that way. Okay, so you can see there. I don't know, why is this not like... Edit expression. Plus 2. 3. There we go. So I don't know why it's not... It's getting confused because this is a pointer. It's like, oh, this must be just like a single pointer, but it's an array. But you can see here that it has the 3. As in fact, here let's just add, so you can see all values. Let's add. So this is just a. So like think of it like plus 0. This is plus 1. I set up 2. Oh, because I'm dereferencing. Sorry. This should be inside. There we go. This one doesn't matter because it's a 0, but I'm still going to put it just for consistency purposes. This is pointer arithmetics. Something that you should learn on your own and be familiar with, just because it will make you a better programmer if you understand pointers better beyond this course. Okay, so I'm taking the address of A and I'm doing the shift by the size of the int. So it's like basically plus 8 bytes here or whatever, plus 12. And then dereferencing that afterwards. Okay, so there's our array. It's kind of easier to see that way. Okay, so when we go ahead and look at this line, we have a 3 and s. So now we're looking at 3 minus 2, or sorry, 3 minus 1, which is 2, which should give us a 4. But you can see that it immediately kind of resets to the next one because now we're deeper in the call in the recursion. So the reason why this like kind of goes crazy is because when it does the function call, it still hasn't filled in the values until like the next line. So it's okay. But yeah, so now we have S2 in there. Now it's going to do 2 minus 1, which is looking at 1. So this spot now, I suppose. I said a plus earlier. I meant a subtraction, my bad. But yeah, okay. So now S has a 1. It's still bigger than 0, so we're just going to keep going a little further. Okay, so look at how many we have in the call stack. We have 1, 2, 3, 4, and 5. Did I ever draw those? Yeah, I kind of did. See? So we have the original 4. Then we have the 3. Then we have the 2. Then we have the 1. And technically we have the 0. This one returned a 0, but it was still a function call. So yeah, we have 5 function calls. And then we have the main. So it matches what we drew. And just like when we did it, now we're comparing 0 here with less than a 0. So now it'll return. So you'll see this will pop 1 out. Well, it first goes to the end of the function there, and then it'll pop it. See? Bam. It popped 1 out. The word pop it's actually a technical word, and we'll talk about it when we call out stacks and queues in the last week of the semester. But yeah, it just means to take something out of the stack. So yeah, as you can see, it immediately brings us back to this line from the previous call. Okay, what happens if I click on these, by the way? Oh, cool! It lets me see. Ooh, that's neat. I never actually clicked on it before. but you can see that it highlights the line where it came from. You can see all these are highlighted the same line because they're all coming from that line from different like instances, but that one is highlighting that line. So very cool, very cool. VS Code, use it or use something else. Don't be coding on Notepad. So yeah, so now we can see that it is returning this. Can we see the return value anywhere? You probably can, but I don't want to mess with this too much. But yeah, so it's going to keep adding it and keep returning it. So you can see the cosx emptying. And finally, we get back from the return value the number of 9, and you get printed. So you can have fun looking at recursion code running like that. Okay, and then thing freaks out because it's like, what is happening right now? What is the code to run after return 0? It's really dry weather now. I need to like wet my lips. Okay. All right. So yeah, that's your example of recursion and following the call stack. And you can see that it all worked out pretty nicely. So I guess for the remainder of the time, we can just do more recursion examples. Let's save this one though. So let me take a moment to look at something. I recall there was one example that I wanted to show. Okay. Aha, yeah. I wanted to show you, okay, perfect. So I want to show you an example of deep copy recursively. Okay, and the reason why is because it might be helpful when you're doing your assignment. So, you know, why not? Plus, it's just it's a little fancier example. So remember with deep copy, the idea if you want to, when you're dealing with dynamic variables and dynamic arrays, if you just try to do an assignment, you just do a shallow copy, and you know, if you change one, it changes the other. So it's probably not what you want. So we're going to do and call it DC for decopy. Okay, and the one I'm going to pass into the function is going to be array1, or we'll call it old and new. Okay, so let's start out by making it a oh crap, can't use new, it's a reserved keyword. So we'll say N and O. Let's start out by making a shallow copy, a lame shallow copy. So it bothers me. I feel like new should be before the old. Let's make it a shallow copy. Bam, that's a shallow copy right there, right? Now I wish I would have made this dynamic. So okay, let's make a dynamic array now. So let's make int for and then b int 4. We you know, they have to be the same size, otherwise the copying won't work anyways, regardless of whether it's iterative or recursive. Don't forget the word new, which we just try to make into a variable name. So, yeah, okay. And let's just fill the arrays with some stuff. I was trying to see if I should do a for loop, but too much effort. Let's just add stuff. Okay, and then let's take the second array, and actually here, let's just not add anything to the second array, and then we'll do the deep copy. Okay, so like for now it's a shallow copy, but let's just go ahead and do it. So deep DC of BA, and then if we were to see out, so let's just do a for loop for this one. For int I is equal to 0, I is less than 4, I plus plus, see out BI, put some space in between them, and then see out inline at the end, run it, and we didn't compile. Semicolon. There we go. So that's worse than I expected, actually. Yeah, okay. The reason why this is happening is it's because it is passing the pointer by value, not by reference. And so when you're doing this, it's basically throwing away the pointer afterwards. So we need to pass in the new pointer at the very least by reference. So yeah, let's do that. So pass the address of the pointer, not the pointer itself. And because we're passing in the pointer, we need to pass to the reference of the pointer again. I think that will work. Oh no, giving way more errors. Okay, maybe just add another asterisk there. Leave that one be. Our errors went down. Int cannot be. Oh, so maybe that was right. Yep. Okay. There we go. So we can see that the numbers are there, present, but it is a shallow copy. And to prove to you that it's a shallow copy, after the copy, I am going to modify a 0 and make it into a 10, and you'll see that on the B it's also a 10. Okay. So the reason why I want to show you this is because of that particular thing. We don't see that often, and we haven't done much examples of like passing by value by reference, at least in a while. And so with pointers particularly, it can get a little tricky to remember. So remember that passing by value is like the default in C++. And if you want to pass by reference, then you need to use the ampersand. And then in this case, I'm actually, technically speaking, I'm still passing by value here. But I'm passing by value the address of this pointer. So when I get the address of that pointer, then I can dereference the address of that pointer and modify the pointer itself. So that's why this works. So yeah, there's that. If I wanted to do true passing by reference, I'd have to do an ampersand up here, which I don't want to do. Okay, so yeah. Now that we've done this, this is a shallow copy, so let's modify this and make this into a deep copy. So if I wanted to do this with a while loop, let's just kind of do that first. So we'll make two versions of the function, and the first one is going to be using a while loop, so we'll call that one WDC. So for that one, it would be something along the lines of like while, well, we need a size variable, so int size, or int s for size. So if I do that, let's do for loop instead. For int I is equal to 0, I is less than size, I plus plus, and then go ahead and modify the indices at I. Okay, so if I do that now, segmentation fault. Ooh, yikes. Well, get rid of that. Why is that one not working? Let's see. OI and NI. So let's see, that's pointing to the address. Oh, I think it's because I need to put parentheses here because of the order of operations. Yeah, there we go. So because the asterisk here, I thought had higher precedence than the square brackets, but it turns out that the square brackets have higher precedence than the asterisk. So we were taking the value of n, let's say just address 20, and then it was adding the value of I, so let's say I is 2, so then it was like n plus 8, so n plus 8 bytes, basically. And remember, these are like hex values, so I guess 20 becomes 28. And then it was trying to dereference that, when that's not what we want. We want to dereference this pointer, and then whatever we get from there, add the 2 to that. So yeah, so be careful about that order of precedence. You know, we want to make sure that the parentheses of it does that first, and then this, okay? So yeah, so I'm actually glad I did that now, because that would have been harder to figure out with the recursion. So you can see now that it works, and the reason why it works is because I changed one of them, but the other one is not affected. You see, now we got a 2, whereas with the shallow copy, if I switch this back to the shallow copy, let's just add a size for now so that it's there. So if I go ahead and switch this to the shallow copy version and I run it, you'll see that I have a 10 because it's modifying, you know, both of them. Deep copy, I have a 2, okay? But the deep copy is using a while loop. I want to use one with the recursive deep copy. So for reference, I guess I'll leave this shallow copy one, I'll call it SDC. And then the deep copy one is just going to be called, well, didn't DC stand for deep copy? Oh, I guess it's recursive. Well, I guess it should be called shallow copy as SC. Yeah, SC for shallow copy. This one for, let's call this one iterative deep copy, and this one for recursive deep copy. There we go. Now we got like a nice naming convention going on. Okay? So let's go ahead and do this. So to do this, you know, what we want to do is, this is our do something, right? So we want to do this something. And then we want to basically advance and copy one at a time as we go through it all the way to the end, right? So what is our recursive case going to be when we reach the end? And again, to avoid having that extra variable, we're going to count down. So when s is less than or equal to 0, that's when we'll know we'll be done. So we'll just return. So that's going to be our base case. And then for the recursive case, it's just going to be RDC. And then we're just going to pass the same values, N, O, and then S minus 1. Okay, I probably need to put an ampersand here. So let's put that. Actually, it might be an asterisk. I'm not sure. We'll see. And then for the copying process, then we're just going to do wherever S is at, but -1, because remember, otherwise it'll be out of bounds. Okay? This doesn't matter if it's here or after. Well, no, it does matter, actually. If I do it there, I'll be okay, I think. Well, no. I think I have to do it beneath, right? It's the same logic as before. Whoa, what just happened? Oh, I think I... There we go. Because I'm doing s minus 1, so when it hits n minus, when the s becomes like 0, and then I'm trying to do it -1 and it crashes, I'm going to be like, what the heck, right? No, I want the if statement to run so that it stops before. So I'm going to put the base case first, then my do something, and then my recursive case. And this it should work, with the exception of trying to figure out if that should be there or not. Okay, so it does not like that being there, so I'm just going to get rid of it. And it worked. Oh, okay, spooky. Why did I need to get rid of that there? I'm not sure. Particularly because I am putting it here. So, but, you know, if it ain't broken, don't fix it kind of thing, right? So let's just let it be. No, actually, I guess the reality is because it's already in this format, so it can stay. It's only here where I need to modify it to actually access. Yeah, okay, that actually makes sense, but I don't need it. Okay. But yeah, so you can see that it works. Now let's try to flip it back so you can see the nasty sec fault we're about to get with a negative number. If you put it like that. No sec fault. Okay, no sec fault, but it's still doing some nasty stuff. I bet you Valgrind will yell at us though. Come on, Valgrind. Be our savior of detecting us doing some nasty code. Well, hold on. Valgrind's gonna yell at us anyways because of the deallocation, but that's okay. Invalid write of size 4. Yeah, so this is definitely it yelling at us. Because we're accessing -1, which means we're accessing 1 before the start of the array. So whatever is before the start of the array is just getting like nasty. So if I do this, it's going to yell at us, but it's not going to yell at us that much. It's going to be memory leak yelling at us. You'll see it. You can see it's like everything is fine. It's just like, hey, by the way, you have a memory leak. That's cool. We know how to fix that. We just go ahead and throw some deletes in here and we'll be ready in no time. And there you go. This is what you want to see. All heap blocks were freed. No leaks are possible. No errors. Nothing detected. All is good in the world. Okay? So another example kind of what we kind of did, because we were already kind of doing the list stuff, but it's kind of important to because this one's a little bit more abstract, but still, you know, you can do it. You know the tools now. It's just a matter of the critical thinking to get you here. So yeah, deep copy recursively. It's a pretty simple code. Well, not simple. It's pretty short, but you can see it can get a little tricky. So I want you to play with this. I want you to familiarize yourself with this. To become strong coder, this should come secondhand to you. And even if you run into issues like I did, understanding how to fix them and why they happened is okay. That's like part of the learning process. But you need to be able to do that. I'm not saying you gotta get things right the first time, but you need to be able to understand how to fix them and why. So, yep. So that's it. That's recursion. If you want to see more recursion examples, please check out previous semester lectures. I try to vary them. Like, aside from the Fibonacci, like I think everything I did this time around is pretty much different. Particularly the coding examples. I think I did palindromes last time and who knows what. So yeah, and I have multiple semesters at this point of 202 recursion. So feel free to check those out. But also, like, there's so many examples online that you can see of recursion, and just try out your own. It's really, like I said it before, recursion is just something that you have to practice so that it becomes second nature. You know, before ending the lecture, I want to close out a note by saying there's programming languages like Scheme where recursion is the only way you do repetition. And imagine that you were in that position, that you learn how to do code recursively and then somebody showed you iterative code. You freak out probably. You'll be like, oh my gosh, what is this? Like, I'm so used to functions. So just because you're the other way around, and you could see, and you could see like them saying like, oh wow, you're like confused at like loops. Like, that's so basic. You know, it's just a matter of like how you learn. Unfortunately, or fortunately, you learned loops first and then recursion. If you were learning the other way around, you would be like, recursion is just like whatever. It's like day-to-day life, everyday life. But you didn't. But don't feel like recursion is just your enemy. It's not your enemy. It's there to help you. In fact, there's disadvantages to using recursion in the first place. So the only real reason you should be using it is because it's helping you. And if it's not helping you, it's because you don't know it well enough yet, because it should help you. And it will, especially in 302, but in general. Recursion is a tool. Use it as a tool to make your life easier, not harder. Okay? Work easier, but earn more money. Yes. Okay? So with that said, thank you for watching, and I hope that you have a great weekend. Take care, and see you next time.